All right, the next thing I want to talk about are what are called the convergents of a continued fraction. So let's look at this example that we had again. We said, okay, well, we had 65 over 23, right? And that was 2 plus 1 over 1 plus 1 over 4 plus 1 over 1 plus 1 over 3. Like that. Which we wrote in notation as square brackets 2. You can use a comma if you want, but some people use a semicolon there. 2, 1, 4, 1, 3. Just the numbers, basically the numbers along the diagonal, which are also, we saw the quotients in the Euclidean algorithm, right? So one thing you can think about is, well, what if I actually decided to cut off and stop? You know, we have this expression, and actually, if you wanted to evaluate it, if you didn't have this number, if you didn't know this number, you'd have to kind of work your way up from the bottom, like 1 plus a third, and then that's 4 thirds, flip it over 3 quarters, plus 4, you know, you get, what is it, like 19 fourths, flip it over 4 19ths. You know, you could recover this number. But going top down, what if you actually stopped? Like, what if I just said, okay, the first 2, that's an approximation. The rest is all a fraction, right? 2 is an approximation to 65 over 23. Or you could stop right here. You could just say 2 plus 1 over 1. That's 3. That's another approximation to 65 over 23. Or I could stop right here and just say 2 plus 1 over 1 plus 1 over 4. Or I could stop right here and do that number. And then there's the whole thing itself. Okay. Those are what are called the convergents. So the convergents are the numbers numbers. I mean, another way you could also write them, by the way, is cutting this off. So you could just say the first one's 2, the second one's 2 plus 1 over 1, the third one's this 2 comma 1 comma 4, which represents 2 plus 1 over 1 plus 1 over 4, right? And so on. So the convergents are the numbers. Let me just write them kind of spaced out. 2 plus 1 over 1, 2 plus 1 over 1 plus 1 over 4, 2 plus 1 over 1 plus 1 over 4 plus 1 over 3. No, sorry, that's a 1. And actually, we do consider the last number a convergent. I mean, I don't know what it's the number itself, but okay. So those are the numbers. Those are what are called the convergents. And if we evaluate these, this one is 2. This one is 3. This one, well, it's 5 quarters, 4 fifths, 14 fifths. This one is, we get 5, 1/5, 6 fifths, 5 sixths. 2 plus 5 6 is 12 6 plus 5 6 is 17 over 6. 17 over 6. 17 over 6. That's an interesting number. Might look back to earlier videos, just think about why. And then we get 65 over 23. So these are the convergents. Okay. And it turns out that these are just really nice, interesting, important numbers, which we're going to see for a couple reasons. First thing is, what are the differences, the deltas among these, right? I want to compute this first. So the first one is 3 minus 2, which is 1. The next one is 14 fifths minus 3, which is 14 fifths minus 15 fifths, which is negative 1/5, right? The next one is 17 sixths minus 14 fifths, which is, if I want to get, you know, common denominator, let me just do it down underneath. So that's 17 times 5 minus 14 times 6 all over 6 times 5 all over 30. 17 times 5 is 85. 14 times 6 is 84. So that's actually equal to 1 over 30. And then this one, 65 over 23 minus 17 over 6. Well, that's 65 times 6 minus 17 times 23, all over 23 times 6. I don't even really care what 23 times 6 is, but 65 times 6 is 390. 17 times 23 turns out to be 9 less than 400, 391. So it turns out this is minus 1 over 23 times 6, which happens to be 138. So these numbers get closer and closer together. Notice the differences are decreasing. I mean, that's one reason I'm talking about this, is the differences are decreasing. They're also alternating, like to go from, so 2 to 3, it goes up, 3 to 14/5 goes down, 14/5 to 17/6, because the difference is positive, it goes up, that goes down. So there's interesting things going on here. And in fact, if we plot them on the number line, so other thing is to notice, like, so things to notice before I even plot them on the number line. The numerators alternate, or the notice in the differences. Let me try to write this better than that chicken scratch that I just wrote. So notice in the differences, the numerators alternate plus or minus 1. And that the difference itself is just sort of as small as it could be between the two fractions, because, right, like, you know, if you have something that's a fifths and something with sixths, that the difference is going to involve 30ths, right? And in fact, it's the smallest possible difference. It's 1/30th, plus or minus 1/30th. A little less obvious here, but denominator 1, so 1 and 5, and it happens to be negative 1/5. Here, denominator 6 and 23, so the difference is going to involve the product, and it's the smallest possible numerator, up to plus or minus. That's sort of interesting. So the difference is sort of smallest possible for the given denominators, meaning the two denominators. And then we can plot. So if I wanted to plot these on the number line, let's just say, let me just put 2 here and 3 here, kind of far apart from each other. Well, this was the first convergent, right? That was 2. The second convergent was 3. I mean, I could call this 2 over 1, I guess. This was, oh, I somehow zoomed in. This is 3 over 1. So going from the first convergent to the second convergent was like that. And then 14/5, that's really 2.8. So, and I'm going to exaggerate the difference because it's probably, you know, it's actually closer to 3 than this. But this is 14 over 5 right there. And we went back this way, minus 1/5, right? Draw that a little steeper, so I'm gonna leave some room in there. And then we had 17/6, which is 1 and 5/6, which is 1.83 repeating. I'm sorry, 2.83 repeating. It's 2 and 5/6, not 1 and 5/6. It's 2.83 repeating. This is 14/5 is 2.8. So again, I'm going to exaggerate the difference a little bit, but this is 17 over 6 right here. And then the last one, and notice we go up by 1/30th, right, to get from 14/5 to 17/6. And then the final one, the number itself, it's actually going to be closer to that one. And this was 65/23. So already we know 65/23 is between 2.8 and 2.83 repeating. We know there's this interesting sort of bouncing back and forth pattern. I'm saying 65/23 is to the left of 17/6 because of the difference being negative here, right? 65/23 is less than 17/6. And it turns out whenever you do continued fraction, you get this sort of nice bouncing back and forth pattern, and that the differences are really small, and it's kind of amazing. And it's like, in fact, there's a sense in which we'll come back to later in the semester, but there's a sense in which the convergents are the best possible rational approximations. Maybe I'll just say it there. Are the sort of and what I'm really going to mean by that is the following. Like, it turns out, for example, that out of all of the fractions with denominator at most 6, this one is closest to this number. And if you keep going, like, just as you get higher and higher numbers, it's kind of like somehow it's like the best possible. You could have all the fifths. You have the fifths. Well, that was supposed to be the fifths. You have the sixths. You have the thirds. You have the halves, the quarters. This one's the best out of all of them. That's closest to that. It'll be more stark when we see like larger denominators and stuff. What's going on, but it's kind of nice. Okay, so that's one thing, is there's this pattern in the plot. So the plotting the convergence gives this sort of oscillating pattern, like a dampened oscillation. You can prove all this in general. I'm just sort of showing you an example and saying, well, this turns out to be true all the time. Another thing that's worth noting, these differences being really small. So look back at this one again. This should have jumped out to you from an earlier video. 65 times 6 minus 17 times 23. We were looking for the inverse of 13 mod 65. We ended up getting the equation 23x plus 65y equals 1. We just found the solution somehow. If I did it with that back substitution in the Euclidean algorithm, but let me just go write this down here. So notice when we did 65/23, so when we subtracted the last two convergents, meaning the next to last convergent and then the number itself, so we had 65/23 minus 17/6. Well, then that was, I'm just writing what we had up there. That was 65 times 6 minus 17 times 23/23 times 6. And this happened to be -1/23 times 6. And so if we isolate just this numerator here, then we have 65, i.e. 65 times 6. Let me write this better. 65 times 6 minus 17 times 23 equals -1. We wanted earlier, we wanted to solve 23x plus 65y equals 1. You could certainly convert this into that, right? So rearrange. I can rewrite that as 23 times -17 plus 65 times 6 equals -1. And then I can just multiply through by -1 everywhere and get 23 times +17 plus 65 times -6 equals +1. And we've recovered, oops. And we've recovered our solution to that linear Diophantine equation. So it turns out that, and again, we should give some justification later, but it just turns out that this next to last convergent actually always gives us the solution. You know, you might have to write out some stuff. You have to sort of count the convergence because of there was the plus or minus 1 pattern here. 1, -1, 1, -1. So you might have to count the convergence and think, okay, what's the, am I going to land on a -1 or a +1? And then you can always just have the numerator set them equal and futz with it. But if you sort of believe the pattern, which is that you're always going to get a 1 or a -1 here, then that actually will always give you solutions. So it turns out this works in general. Something we should justify. Out. This works in general. We can always use the next to last. So yeah, if we're trying to find, to solve ax plus by equals 1, so let's just assume a and b are relatively prime, you can always look at the next to last convergent. We can use the next to last convergent as, I'm not going to, I'd have to write it out much more carefully, but when I say the word use, I mean use it like we did above. The next to last convergent of, let's just say b over a. Suppose b is greater than a. It doesn't really matter. You could actually do it the other way around. But yeah, say b is greater than a. Okay, and so this is kind of amazing. It turns out this works if you believe these patterns, which again, I showed you one example. So, but we're gonna have to, I'll make you do more examples so that we can actually see this is happening, and we'll try to give some proofs. But it's pretty cool. It's a pretty cool way to solve that. Basically, you just find the continued fraction and you compute the next to last convergent, and it turns out that will give you the numbers you need to solve the linear Diophantine equation. That's still a little tedious, and there's actually an even better way. There's like a really fast algorithm to let you calculate convergence that we'll talk about soon. Okay, I'll stop.